Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 1st, 2026, about 1 week ago. It finds that self-organizing teams of large language models consistently fail to beat their single best member, underperforming that expert by roughly 8 to 38%. The paper's titled, Multi-Agent Teams Hold Experts Back. And as we'll see later, the implications for how we align models using human feedback are quite significant. So, Figure 1 illustrates this core problem through 3 key observations. On the left, the synergy gap appears where the team's performance actually trails behind the top expert, meaning strong synergy is completely missing. The middle panel explains why this happens. Instead of deferring to the knowledgeable agent, shown here with a PhD cap, the group defaults to compromise. Finally, the right side shows that as you add more members, this expertise dilution gets worse, dragging performance down toward the average. Moving to the results, Figure 2 shows performance on the lost at sea task, where lower bars mean better scores. The orange bars represent the single best expert working alone, and they consistently set the gold standard. In contrast, the red bars show how teams perform when the expert is explicitly revealed. Despite this knowledge, teams cannot match the expert's solo performance, meaning they fail to defer. Even more telling, the red bars are barely lower than the gray bars, where the expert was not mentioned at all, suggesting that simply identifying the expert solves almost nothing. Well, Figure 3 takes this a step further by illustrating the expertise dilution effect on the NASA moon survival task. Here, the graph plots ranking error on the vertical axis against team size on the horizontal axis. Notice that as the group grows from 2 agents to 8, the error rate climbs steadily upward. This negative trend persists across all model compositions, shown by the red, blue, and green lines. It seems that adding more voices simply adds more noise, drowning out the expert's signal because the group prioritizes compromise. Alright, Table 1 expands this analysis to all 3 human psychology tasks, covering both concentrated and distributed expertise. The values here represent the relative synergy gap, which is the percentage increase in error compared to the best individual expert. You can see that every number is positive, confirming that teams consistently underperform. Looking at the concentrated expertise columns on the left, even when the expert is explicitly revealed, the error gap remains high, sitting at around 82% for NASA moon survival. The distributed expertise section on the right shows even larger losses, proving that teams struggle to integrate knowledge regardless of how it is distributed. So, moving beyond psychology tasks, Table 2 examines how these teams fare on frontier machine learning benchmarks like Simple QA and Math 500. The column labeled at least one correct establishes the theoretical ceiling, showing what the score would be if the team perfectly listened to the agent with the right answer. Yet the far right column reveals substantial relative synergy gaps, ranging from 8% on MMLU Pro to nearly 38% on Humanities Last Exam. This confirms that the failure to leverage expertise is not just a quirk of psychology games, but a consistent issue in technical domains as well. Well, to understand the mechanism behind these failures, Figure 4 provides a concrete transcript from the NASA moon survival task. In the middle panel, Agent 1, the expert, demonstrates strategic persistence. They use domain knowledge about spacesuits to argue against moving a heating unit up the priority list. Yet, look at Agent 2 at the bottom. Instead of deferring to this expertise, they offer an integrative compromise, proposing a middle ground ranking that ignores the expert's factual correction. This insistence on finding a balance, rather than accepting the truth, is what ultimately holds the team back. Alright, while the previous figure showed a single conversation, Table 5 now confirms that pattern statistically across all tasks. It lists correlations between behavioral events and the synergy gap, where positive values indicate the team performed worse than the expert. Looking at the non-expert events on the left, epistemic deference shows strong negative correlations, meaning performance improves when non-experts simply yield to the expert. In contrast, integrative compromise has high positive values, proving that seeking a middle ground consistently hurts the team's score. On the right side, the data for experts is equally telling. Epistemic flexibility correlates with worse outcomes, because when experts back down to be agreeable, the team loses the correct answer. Wrapping up, 2 main takeaways stand out from this research. First, simply grouping powerful models into teams does not automatically yield better results. In fact, the pressure to be agreeable often dilutes the best answers. This points to a critical trade-off in how we currently train models. The same safety alignment that makes agents polite and robust against sabotage also prevents them from deferring to genuine experts. To unlock true collective intelligence, future systems must move beyond simple consensus and learn when to let the smartest agent lead. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.